There's a bunch of isotope standards. For stable isotopes, principally, we get material from the International Atomic Energy Agency, the NIST, the National Institute of the Bureau of Standards. It has a lot of reference materials, not so much for stable isotopes, but for a lot of other isotopes, and a lot for chemical analyses, and some of which are homogeneous enough that they can be handy to use for isotope reference materials, again, especially of metals. So the standards, okay, these are the absolute values, and you can see how, I'm not sure if you wanted to talk about absolute values of things, it's more convenient to talk about relative values rather than saying, oh, our water has a value, deuterium hydrogen ratio of 0.002-00520. It's easier to say 0 per mil. Okay, so the isotope reference material, SMO, is something called standard mean ocean water. And this was a sample that Harmon Craig concocted while he was on sabbatical in Pisa, Italy, and distributed to his friends. And it wasn't really intended to be the standard for the next 50 years, but it is. And it's all gone. And SMO, at that time, they had thought that they had a pretty good idea of what the isotope value of the ocean is. It's been measured in a bunch of different places. It's different in the Mediterranean, deep Atlantic, shallow Atlantic, and so on. So they concocted a bottle of water that was about that value, and that's why it's called standard mean ocean water. Vienna SMO, or VSMO, is a water, again, a synthetic water that has almost as well to like within 0.1 decimal point of the original value. So this is the standard that you can buy with a little vial about this big that costs about $500 or something like that. So you don't want to use it a lot. You want to have your own reference material. So we have made up a bottle of our own, just mixing a bunch of different waters to get something we use in the lab that's about that value. And we have our standard tap water from from this building that is a very, very different value on the scale, and we've referenced both of those to the international standards, and that's our everyday standards. And Craig and Shavankar will talk about these things in detail. Other things, PDB belemnite, this is the carbon scale. Again, the original stuff is all gone, sorry. Air is used for helium and nitrogen, and fortunately, the atmosphere is not all gone. So actually just air is used, and it's homogeneous in both of those things, unless you're in a city, okay, or unless you're collecting your helium sample, say, in the lab where helium tanks are open. Again, there was a paper published saying the helium isotope value of the atmosphere was changing, and that's because somebody had been collecting helium over a 20-year period inside of a building, inside of a chemistry building. And they noticed that there was getting to be more helium-4, and they said, well, but it turns out the inside of the building was not representative of the planet. So again, don't do silly things and put your name on it. And especially don't publish it. Canyon Diablo troilite is just a meteorite that fell in formed meteor crater. So these are other reference materials that are available. Well, some of them are no longer available, but are commonly used. But again, various labs have their own internal reference materials that you use for your everyday run-of-the-mill samples. So these, you want to maybe use these once a year to make sure your lab is not having something going on. Okay, so again, just a list of standards, and ask questions of the people who know as we go forward. Okay, and this is the difference between the PDB and the SMO standards. Okay, which, as I said, if you're doing capital delta discussions, makes a difference as to which standard you're actually using, because the original material has different isotope ratios. And if you get into CO2 and carbonates, this is actually a diagram you will probably want to come back to understand how carbonate values are derived. I know some of you are working on carbonates for your thesis, or perhaps for something else. Okay, other ways to separate isotope exchange reactions. Okay, I've introduced you to this. Okay, these are exchange reactions, and these represent equilibrium reactions. Okay, there are other ways in which we can separate isotopes. There are several kinetic effects. So a kinetic effect, this is something called Graham's law. And if we just think about a flux that's related to velocity of molecules, so we'll just take the situation. Remember that E, energy, is equal to 1/2 mv squared. Okay, the standard kinetic energy reaction. So if we have a molecule, gas molecule in the air, it has a kinetic energy that's related to the temperature of the system. Okay, so let's just consider carbon dioxide in the atmosphere, and we could look at a case where energy of molecule 1 is the same as energy of molecule 2, and in these two cases it would be the reduced masses. So if we compare mass 45 to mass 44, the difference in velocities should be about 1.011, which is 11 per mil, which is big. Okay? So examples where this is important is if you have an alkali solution, like a pH of 10 or 11, then the molecules hitting that surface are going to be affected differently. Okay? And some examples. Hugh Barnes and Jim O'Neill found these really cool alkaline springs, pH 12 and 13 in California. And then Clark in Oman. And so these had really high pH values, and they had a big isotope effect. I'm just showing data here from these are stalactites that grow on bridges, okay, over a period of time. So you build a bridge, a concrete bridge, it rains, the stuff seeps through the concrete isn't quite cured. You actually get stalactites growing in the bottom of bridges. And Krishnamurthy wrote a nice paper on these. And look at these weird isotope values. So the carbon-13, minus 25 per mil, minus 23 per mil. These are all growing in the air. The air at the time is minus 7 per mil. So we're getting these huge isotope effects related to these stalactites that are growing in these alkaline solutions. So we can get huge isotope effects related to this kinetic effect. There's another effect called the that's related to the difference in diffusion coefficients, and this is known as Fick's law. And sometimes, and again, you'll see that Fick's law is a difference in the diffusion coefficients, and sometimes it's confused with Graham's law, which I just described. Fick's law is different. It's a difference in the diffusion coefficients, and it's related to these reduced masses in sort of the same sort of a form, except that there's not a squared, well, the mass is a squared term this time, and the diffusion coefficient, okay, is what a molecule sees when it sees and reacts with all the other molecules that it's diffusing through. Okay? So these are a bunch of parameters in the diffusion coefficient, but the bottom line turns out to have an interesting effect, and that is that diffusion for carbon 12 CO2 versus 13 CO2 has an effect of, it's not just the mass of the molecule, it's affected by the mass of all of the other molecules in the air, which in this case are mostly nitrogen. Okay? So the reduced mass is different than in the other case. So instead of 11 per mil, we have a 4 per mil isotope effect. So this is a diffusion coefficient. This is incredibly important in some of these systems. Leaf stomata Diffusion is a very important parameter. Soil gases, some aquifers. Okay, so these will be in some later lectures in the course. Another process is Rayleigh fractionation, and this will be the topic of the lecture tomorrow with Jim Elringer and Dave Bowling. Rayleigh fractionation is something that if you are depleting apparent mass, something by an equilibrium process, okay, but you extract things in a ratio different than are present in the parent, you'll change the parent that's left over just by taking away ratios of things that are different. And so Rayleigh worked this out about 200 years ago. And the ratio is something is equal to its initial ratio times the fraction of things remaining times 1 minus alpha, where alpha is this equilibrium fraction effect. Okay? And this is true for trace elements. It's true for trace isotopes. Okay? And the vapor fractionation curve for water is a great example. So here we have a picture from my apartment in Cape Town when I was on sabbatical. We have the ocean with 0 per mil. Okay? The ocean has a surface, has a temperature of about 25 degrees here. 25 degrees here is an isotope difference of about 9 per mil. Okay? So the vapor is 9 per mil depleted in oxygen 18 compared to the surface ocean water. Okay? So this represents our starting condition. So we start out equilibrium fractionation, and now we move. So we're going to take our storm, and we're going to start here, and we're going to successively extract water. So the vapor is -9. The liquid it's in equilibrium with is 0. Okay? So let's repeat. The vapor is -9. The liquid is 0. And it's in equilibrium. Now we're going to not let it see the ocean anymore. Okay? So the very first drop of water that condenses from the -9 liquid must have a value of I couldn't hear. Okay, the liquid is 0, the vapor is -9, it's in equilibrium. Now it's going to no longer see the ocean. Okay, so we're going to move away from the ocean, can't see it anymore. The vapor is -9. What's the equilibrium liquid? 0. Right, so it's 0. So if we take this ratio away, this liquid water, from the vapor, then the vapor is no longer -9 because we've taken some of the heavy isotopes away. Okay? So if we were here, we're going to move down this curve. We're going to successively extract liquid that's 9 per mil enriched, and every time we take some away, that means the vapor left behind is going to be a little bit lower. So these are the two parallel curves, and I just show them as always -9 per mil separated. Okay? By the time we get to Salt Lake City, where you guys were yesterday, if you would have been there in the winter, the vapor, okay, the first rain that forms in Cape Town, a very strange storm that moves from Cape Town to Salt Lake City to Antarctica, but you can do anything graphically. Okay, by the time we get to Salt Lake City, the precipitation is about -10, the vapor is about -25. Okay, if we keep going down here, we get colder and colder, we extract more and more water out of this system, we're going to get down to -30 or -40 per mil values. Okay? Now, the other thing to remember is if a cloud is at saturation and never receives any more water, how do we get more water out than we've got out before? How do we get water out of a cloud? We have to cool it. We have to cool it more than it's ever been cooled before. If we heat it up again, it doesn't get any more vapor, nothing is going to come out. Vapor can only come out when it becomes supersaturated. okay? So if we have a single pass cloud, okay, it'll follow these kind of trajectories, okay? So in real life, we rarely have a system that behaves that perfectly. So if we take a storm system that starts in California and it goes up over the Sierras, it actually is pretty much like this. But then as it keeps coming across the western mountains and other places, it'll actually get more vapor injected from evapotranspiration and evaporation of water bodies. And so real clouds are more complex than the single pass system. Okay? And Gabe will discuss a bunch of that tomorrow.